Most people carry a quiet assumption about the world they live in, that the map on their phone always knows where they are, that the delivery truck arrives on time, that the plane lands where it is supposed to land. This assumption is so deeply embedded into daily life that it rarely rises to the surface of conscious thought. It simply exists, like gravity, like electricity, like the idea that water comes from the tap when you turn the handle. And like all assumptions built into the foundation of modern civilization, it is worth examining carefully because the foundation is more fragile than it appears. GPS, the Global Positioning System, is a network of roughly 30 satellites orbiting Earth at approximately 20,000 kilometers above the surface. Each satellite continuously broadcasts a precise time signal. Your device receives signals from at least 4 of these satellites simultaneously and calculates your exact position by measuring the tiny differences in arrival time between those signals. The math is elegant. The system is elegant. But elegance, as engineers often note, is not the same as resilience. When people imagine GPS failing, the first image that comes to mind is a driver staring at a blank phone screen, unsure which turn to take. At first, this seems small, inconvenient, perhaps mildly stressful, but nothing a paper map or a local question couldn't solve. This is the first layer of the assumption that GPS is a navigation tool for individuals, something you use when you don't know the way. But that framing misses almost everything important about what GPS actually does in the modern world. GPS is not primarily a navigation aid. It is a timing system. The positioning function that most people associate with the technology is, in the broader infrastructure sense, almost secondary. The truly critical function of GPS is its ability to deliver extraordinarily precise time synchronization to systems that cannot function without it. Telecommunications networks, power grids, financial transaction systems, internet routing protocols, air traffic control, cellular towers, the stock exchange. These systems do not use GPS to know where they are. They use GPS to know exactly when they are, to the microsecond. To understand why this matters, consider how a cellular network operates. Dozens of towers in a given city all transmit signals in the same frequency bands. For this to work without catastrophic interference, every tower must synchronize its transmissions with extreme precision. They coordinate using GPS timing signals. Remove that coordination, and the towers begin to drift. The interference builds. Call quality degrades. Data transfer slows. Over the course of hours, in a serious GPS disruption, urban cellular networks begin to collapse from within. Not because the towers are damaged, but because they have lost their shared sense of time. The same principle applies to financial systems. Modern high-frequency trading, international fund transfers, and transaction verification all rely on time-stamping accurate to microseconds. Banks and clearinghouses use GPS synchronized clocks to sequence transactions, detect fraud, and reconcile ledgers across institutions that operate in different locations and time zones. In a GPS outage, these clocks begin to drift relative to each other. At first, the discrepancies are invisible. Then, they become anomalies. Then they become errors. In a sustained outage lasting more than a day, the integrity of financial transaction records comes into serious question. Most people focus on the obvious impact: the navigation apps going dark, the rideshare drivers pulling over, the logistics apps freezing. These are real and immediate. But they are the surface layer. Beneath them, a quiet cascade is already beginning, moving through systems that the average person never thinks about and rarely sees. The power grid is perhaps the most sobering example. Modern electrical grids, particularly those that span large geographic regions, use GPS timing to coordinate the synchronization of power flowing from dozens of generating sources into a single interconnected network. This synchronization, called phase alignment, must be maintained within fractions of a second. Grid operators use GPS, synchronized phaser measurement units, PMUs, to monitor the health of the grid in real time and make rapid adjustments. Without GPS timing, these measurements become unreliable. Operators lose situational awareness. The grid doesn't immediately fail, but it becomes harder to manage, harder to protect, and more vulnerable to cascading faults. The margin for error shrinks dramatically. Now, zoom out for a moment, not just to your city or your country, but to the global supply chain that moves goods, food, fuel, and raw materials across every ocean and every continent every single day. Modern cargo shipping relies on GPS for navigation, obviously, but also for something less visible: automated port operations. Container terminals in major ports use GPS-guided cranes, automated guided vehicles on the dock floor, and real-time vessel tracking to manage the flow of thousands of containers per day with minimal human intervention. In a GPS outage, these automated systems halt or revert to manual operation. Throughput drops dramatically. Ships wait at anchor. Containers sit on docks. Schedules collapse across the entire downstream supply chain. Consider what this means for a country that imports the majority of its food, or a manufacturing hub that depends on just-in-time delivery of components from overseas suppliers. The disruption doesn't feel like a system failure at first. It feels like a delay, then a shortage, then a price spike, then a crisis. Each step follows from the last, not through catastrophe, but through simple arithmetic. When the flow of goods slows, the buffer provided by existing inventory gets consumed. Once inventory is gone, the next step is absence. Aviation deserves particular attention because the dependency on GPS in modern air travel is both deep and specific. The older navigation system, ground-based radio beacons known as VORs and DMEs, still exists in many countries, but has been progressively decommissioned over the past 2 decades as GPS-based approaches became the standard. Many airports, particularly regional ones, have GPS as their only precision approach system. In a GPS outage, these airports effectively close to instrument flight. Aircraft that are already in the air can continue navigating using inertial navigation systems, which maintain accuracy for a number of hours before drift becomes significant. But new departures, approaches in low visibility, and oceanic routing all become dramatically more complicated or simply impossible. Air traffic control systems that have been upgraded to use GPS for surveillance, knowing where aircraft are, must revert to radar only, or in some regions where radar coverage is sparse, must simply reduce the number of aircraft they manage at any given time. The system doesn't crash, it contracts. Flights are delayed, rerouted, canceled. The economic consequence is enormous. A single day of disruption across a major continental airspace produces losses in the billions, not from destruction, but from standstill. At this point in considering the scenario, a reasonable person might ask, how realistic is this? Could GPS actually go dark? The honest answer is that full system failure is unlikely, but not impossible, and partial or regional disruption is well within the range of historical precedent. GPS jamming, deliberate interference with GPS signals, has been documented in conflict zones and their surrounding regions for years. In parts of Northern Europe, GPS interference has occasionally disrupted civilian navigation and aviation for brief periods, traced to military activities in nearby areas. The signals are not difficult to jam. A sufficiently powerful broadcast on the right frequency from the ground can overwhelm the relatively weak signals coming from orbit. Spoofing is a more sophisticated and more dangerous variant. Rather than blocking GPS signals, spoofing replaces them with false signals, convincing a receiver that it is somewhere it is not. There are documented cases of ships in the Black Sea receiving spoofed GPS coordinates that place them tens of kilometers inland. There are documented cases of aircraft receiving false position data near conflict zones. Spoofing is harder to detect than jamming because the receiver continues to function and display confident, plausible data. The danger is not that the system goes dark. It is that the system becomes a reliable source of false information. Then, there is the geophysical dimension. The sun is not a passive background feature of the solar system. It produces periodic bursts of charged particles and electromagnetic radiation, coronal mass ejections that interact with Earth's magnetic field and ionosphere. In 1989, a geomagnetic storm caused by solar activity knocked out the Hydro-Quebec power grid, leaving 6 million people without electricity for up to 9 hours. In 1859, the Carrington event, a much more powerful geomagnetic storm, produced currents strong enough to set telegraph equipment on fire. The modern world is orders of magnitude more dependent on electronic systems than it was in either 1859 or 1989. A Carrington-level event today would likely damage or destroy a significant portion of the satellite infrastructure in low and medium Earth orbit. GPS satellites orbit in medium Earth orbit, which sits within the outer Van Allen radiation belt, one of the most energetic zones of charged particles during a major geomagnetic storm. Satellite operators would attempt to put their birds into safe mode, but the radiation environment during an extreme event might cause hardware failures regardless. Even if the satellites survived, the ionospheric distortions caused by the storm would severely degrade GPS signal accuracy for days to weeks, making the system unreliable even where technically operational. This is not a science fiction scenario. It is a recognized risk that space agencies and civil aviation authorities have studied and modeled. The question is not whether a major solar storm will occur. The question is when and how prepared the systems that depend on GPS will be when it does. What happens in the first hour of a serious GPS disruption is, paradoxically, very calm. Most people don't notice. Navigation apps display a frozen position or show a brief loading indicator. Systems with internal clocks continue operating on their last synchronized time. Aircraft in the air continue flying on their previously computed routes. The grid continues running. The ports continue processing. Nothing dramatic happens in the first hour, which is part of what makes the scenario so analytically interesting. The disruption is invisible until it isn't. By the fourth or fifth hour, the first ripples become visible to professionals, if not to the public. Air traffic controllers begin noticing inconsistencies in position reporting. Port operators begin seeing errors in automated vehicle guidance. Cellular network engineers receive alerts about synchronization drift. Power grid operators notice degraded PMU readings. Financial system administrators begin logging timestamp anomalies. Each of these groups is working on their specific problem in isolation. Most assume it is a local issue, a system bug, a sensor fault. The systemic cause is not immediately apparent because each system has its own monitoring layer that filters out the underlying signal. Between 12 and 24 hours into a sustained outage, the responses begin to diverge. Well-prepared systems activate backup protocols. Aviation authorities issue NOTAMs, notices to airmen, restricting certain types of operations. Power grid operators increase staffing and switch to more conservative management modes. Banks and financial institutions freeze certain categories of automated transactions and escalate to manual review processes. These responses are not seamless. They are slow, expensive, and imperfect. But they represent the layer of resilience that decades of infrastructure planning have built into critical systems. Less well-prepared systems begin to show visible strain. Smaller carriers and logistics companies that rely entirely on consumer GPS devices for fleet tracking lose visibility of their vehicles. Cold chain logistics, the refrigerated transport of food, medicine, and biological materials, faces particular challenges as route optimization and temperature monitoring systems tied to GPS lose synchronization. Some shipments are delayed at customs because automated cargo tracking systems cannot confirm their location history. Others are simply lost in the operational confusion. Zoom out further and consider the agricultural dimension, which almost never appears in mainstream discussions of GPS dependency. Modern industrial farming relies on GPS-guided precision agriculture to an extent that would surprise most people outside the industry. Tractors equipped with GPS autopilot systems maintain centimeter-level accuracy when planting, fertilizing, and harvesting crops across large fields. The efficiency gains from this technology are significant. Reduced overlap, reduced chemical waste, optimal row spacing, nighttime operation. In regions where the planting season is narrow and the weather window is short, losing GPS guidance for even a week during a critical period can reduce yield or delay harvest in ways that affect food supply months later. The secondary effects on supply chains are compounded by a factor that is easy to overlook: trust. When GPS-based logistics systems fail, The first response of many operators is to assume the data is temporarily unavailable. The second response is to assume the data is unreliable. Once operators stop trusting their positioning and timing data, even partially, they begin making manual decisions that introduce inefficiencies far beyond the direct technical failure. Shipments are held pending verification. Routes are adjusted conservatively. Deliveries are rescheduled. Each individual decision is reasonable. Their aggregate effect is a dramatic reduction in logistics throughput across an entire system. Consider the human behavior layer during an extended urban GPS disruption. The initial response in cities is confusion rather than panic. People who have not used a paper map in years find themselves unable to navigate unfamiliar areas. Rideshare services stop accepting new rides. Delivery drones, used in some urban environments for small package delivery, are grounded. Urban cyclists using shared bikes with GPS locks are unable to unlock them. These are minor inconveniences in isolation, but together they represent a sudden, sharp degradation in the ease of movement through urban space that modern cities have quietly come to depend on. Emergency services deserve particular attention in this context. Police dispatch systems, fire response routing, and ambulance coordination have all been progressively integrated with GPS-based mapping and tracking. In many modern emergency response centers, dispatch software automatically assigns the nearest available unit to an incident using real-time GPS positioning. When that positioning data disappears, dispatchers must revert to radio check-ins and manual map boards. Response times increase. Coverage gaps emerge. In a dense urban environment during an extended disruption, the strain on emergency services is real and measurable. There is a dimension of this scenario that tends to be discussed only in specialized policy circles, and it concerns the military and geopolitical implications of GPS vulnerability. The United States military, which operates and funds the GPS satellite constellation, has spent decades integrating GPS into weapon systems, force coordination, logistics, and intelligence. Other major military powers have developed their own satellite navigation systems. Russia's GLONASS, the European Union's Galileo, China's Beidou, partly as a strategic hedge against dependence on a system controlled by a potential adversary. In a future crisis scenario, the deliberate degradation or denial of GPS signals over specific regions is not merely a theoretical possibility. It is a recognized tool of modern conflict. This creates an interesting policy paradox. The more deeply civilian infrastructure integrates GPS into critical systems, the more attractive GPS disruption becomes as a lever of pressure in geopolitical disputes. And the more attractive that lever becomes, the more important it is for civilian infrastructure to develop independence from single-point navigation and timing dependencies. But building that independence is expensive, technically complex, and politically unglamorous, which is why it tends to get deferred in favor of more visible infrastructure investments. The good news, to the extent that this scenario has a hopeful dimension, is that backup systems exist. ELORAN, an updated version of the older LORAN radio navigation system, can provide timing and positioning over large geographic areas without satellites. Chip-scale atomic clocks, which maintain accurate time for long periods without external synchronization, can be installed in critical infrastructure nodes. Inertial navigation systems can maintain aircraft and vessel positioning for extended periods after GPS loss. Fiber optic timing networks can distribute precise time across telecommunications and financial systems independent of satellite signals. None of these technologies are new. All of them are deployable. The barrier is not technical, it is organizational. Some countries have moved further on this front than others. South Korea, after experiencing repeated GPS interference events from across its northern border, invested substantially in ELORAN infrastructure as a backup system. The United Kingdom has conducted serious policy analysis of GPS dependency and published detailed assessments of the risks to critical national infrastructure. Several European nations have incorporated GPS-independent timing requirements into their grid and telecommunications resilience standards. These are not dramatic interventions. They are quiet, methodical engineering decisions made by people who took the risk seriously enough to act on it. The realistic near-future scenario, given current trajectories, involves not a single catastrophic GPS blackout, but rather a gradual increase in the frequency and severity of localized disruptions. Jamming events near conflict zones that spill over into civilian airspace, spoofing incidents in shipping lanes and ports, occasional ionospheric disturbances affecting GPS accuracy during periods of elevated solar activity. Each of these events will function as a stress test of existing resilience measures. Some systems will handle them gracefully, others will not. The pattern of failures will reveal the actual weak points in the infrastructure, as opposed to the assumed weak points. The economic case for resilience investment becomes clearer each time a disruption occurs. A single event that grounds aviation over a major hub for 24 hours costs the industry hundreds of millions of dollars. A spoofing incident that causes a large container vessel to run aground costs tens of millions directly and delays supply chains for weeks. A GPS timing anomaly that corrupts financial transaction records for even a few hours requires thousands of hours of audit work to untangle. These costs are not hypothetical. They have already occurred in various forms. The question is whether they are occurring with enough frequency and visibility to force the organizational response that the technical analysis has long recommended. There is a broader observation embedded in this entire scenario, one that goes beyond GPS specifically. Modern civilization has built extraordinary efficiency into nearly every system it operates. Supply chains, energy grids, financial networks, communications infrastructure, transportation logistics. This efficiency is real and valuable. It has raised living standards and reduced waste across the global economy. But efficiency is not the same as resilience. In fact, efficiency and resilience exist in a fundamental tension. The most efficient supply chain carries no buffer inventory. The most resilient supply chain carries substantial buffer inventory. The most efficient grid operates at high utilization with minimal redundancy. The most resilient grid operates with significant spare capacity and multiple fallback pathways. GPS is simply the clearest and most legible example of this tension in contemporary infrastructure. The system is extraordinarily efficient at delivering timing and positioning services to an enormous number of users simultaneously at near zero marginal cost per user. The efficiency is so compelling that virtually every sector of the modern economy has incorporated it without fully mapping the consequences of its failure. The dependency grew not through a single decision, but through thousands of incremental decisions, each individually rational, whose cumulative effect was a structural vulnerability that no single person or organization planned for or fully owns. Now consider what a full week without reliable GPS looks like at the level of the individual city. Not a mega city, not a capital, but a mid-sized regional hub. The kind of place that processes goods for a surrounding region, where hospitals serve several neighboring districts, where the commuter rail connects to longer routes, where the port or airport handles a modest but continuous flow of freight and passengers. This scale of city reveals something important about how GPS dependency is distributed unevenly across population centers of different sizes. In the first 2 days, the city manages. Emergency protocols are activated. The regional airport restricts operations to visual flight conditions only. The train system continues running because rail signaling in most countries still relies on fixed point sensors rather than GPS, though the scheduling software that optimizes train spacing and reduces delays begins producing errors that accumulate over time. Trucking companies revert to paper manifests and phone-based coordination with drivers. Pharmacies begin to notice that their automated restocking systems, which rely on GPS synchronized supply chain software, are no longer generating accurate orders. Hospital inventory management systems log warnings, but continue functioning on cached data. By day 3, the friction is becoming visible to ordinary residents. Deliveries are late. Certain medications are running low at pharmacies. The fuel station at the edge of the city reports that a scheduled delivery didn't arrive because the tanker truck dispatcher lost coordination with the driver. The city's waste management department begins manually routing garbage collection, which takes longer and leaves some areas uncollected. These are not catastrophic events. They are operational degradations, the kind of thing that, in isolation, would be a minor inconvenience. Together, they begin to accumulate into something that feels different. Not a crisis, but the recognizable texture of a system under stress. By day 5, the city's hospital administrator is on the phone with regional health authorities, not because patients are dying, but because the surgical supply chain has thinned enough that elective procedures are being postponed. The hospital's blood bank is managing carefully because the refrigerated logistics system that normally ensures just-in-time delivery of blood products has been disrupted, and buffer stock is limited. The administrator is making decisions that under normal conditions would be handled automatically by software. She is doing it carefully, methodically, and successfully. But the cognitive load is significant, and she is one of dozens of managers across the city doing the same thing simultaneously. This is what a week without GPS actually looks like at the operational level. Not collapse, not chaos, but a steady accumulation of friction, delay, and manual intervention that consumes enormous human effort and organizational capacity. Capacity that would, under normal conditions be directed toward growth, improvement, and service. The city keeps running, but it runs harder, slower, and more expensively than it did before. Now extend that scenario to a month. The landscape shifts considerably. At 1 month, the systems that activated emergency protocols in the first week begin to show the limits of those protocols. Backup procedures designed for short-term use are not always sustainable at scale. Manual coordination processes that work for a few days become exhausting and error-prone over weeks. Staff who were redeployed to cover GPS-dependent functions begin to experience fatigue. Training gaps emerge. Younger workers who never operated without GPS-assisted tools lack the instinctual knowledge that older colleagues carried from an earlier era of infrastructure. The agricultural consequence becomes more concrete at 1 month, particularly if the disruption spans a planting or harvest window. A farmer operating across several hundred hectares with a GPS-guided tractor can manage with manual driving, but the efficiency loss is substantial. Rows are less precise. Overlap in chemical application increases input costs. Night operations become impossible without GPS guidance because human visual navigation in darkness across a large field is not reliable. The cumulative effect across a major agricultural region during a critical seasonal window translates into yield reductions that appear in food prices 3 to 6 months later, long after the GPS disruption itself has been resolved and largely forgotten by the general public. The international dimension of a month-long disruption introduces a layer of geopolitical complexity that is worth examining carefully. Countries that operate their own satellite navigation systems, Russia, China, the European Union, would be less affected if the disruption were localized to the American GPS constellation. But the global logistics and financial infrastructure is so deeply integrated around GPS specifically as the oldest and most widely adopted system that even countries with alternative systems would experience significant secondary effects. Most commercial aircraft are certified primarily around GPS receivers. Most shipping vessels carry GPS as their primary positioning system. Transitioning to GLONASS, or Beidou, at scale requires software updates, equipment recertification, and retraining, none of which happens quickly. This illustrates a principle that is easy to overlook in discussions of navigation system redundancy. Having multiple satellite navigation systems available is not the same as having resilient infrastructure. Resilience requires that the backup systems be genuinely integrated into operational procedures before the failure occurs. That pilots are trained on them, that dispatch software is certified for them, that port automation systems can switch between them smoothly. In many cases, this integration exists only partially or theoretically. The redundancy is on paper. The operational reality is that GPS is the system everyone actually uses, and the alternatives are familiar to specialists, but not to the broader operational environment. There is a generational dimension to this problem that rarely gets discussed. The engineers who designed and maintained the infrastructure of the 1970s and 1980s built systems that assumed GPS didn't exist because it didn't. They carried in their professional knowledge a set of practices: celestial navigation, dead reckoning, manual signal timing, map and compass land navigation, that were simply the tools of their trade. That knowledge didn't disappear immediately when GPS arrived. It persisted in the workforce for decades, gradually fading as new professionals entered who had always worked in a GPS-enabled environment and had no practical experience with the alternatives. Today, in most sectors of infrastructure, the generation that operated without GPS is retired or near retirement. The institutional knowledge that allowed graceful degradation in earlier eras, the ability to fall back on pre-GPS methods without significant loss of function, has become rare and unevenly distributed. Some sectors have recognized this and maintained training programs explicitly designed to preserve backup skills. Military aviation, for instance, continues to train pilots in non-GPS navigation precisely because the military understands the vulnerability. But in commercial aviation, merchant shipping, and civilian logistics, the economic incentive to maintain backup skills is weaker, and the investment in preserving them is correspondingly limited. This is not a criticism of the people who made those choices. It is a description of how rational economic decisions, made independently by thousands of organizations over decades, can produce a collective outcome that no single organization intended or would have chosen if they had seen the full picture. It is, in a sense, a coordination problem. Any individual airline that invested heavily in non-GPS navigation training would bear the full cost of that investment, while sharing the benefit of a more resilient aviation system with all other airlines. The incentive structure discourages the investment, even though the aggregate outcome of universal underinvestment is worse for everyone. Understanding this coordination problem points toward the kind of institutional response that is actually capable of addressing it. Individual organizations, acting on their own economic incentives, will systematically underinvest in resilience against low probability, high consequence events. Addressing this requires either regulation, mandating backup systems and training, or pooled risk mechanisms that change the economic calculus for individual actors. Both approaches have been used successfully in other domains. Aviation safety regulation has made commercial air travel extraordinarily safe, not because airlines are altruistic, but because regulators have consistently mandated standards that individual airlines would not have adopted voluntarily. The same logic applies to GPS resilience. The satellites are still up there for now, broadcasting their quiet time signals to a world that has learned to take them for granted. The grid is running, the planes are landing, the ships are moving through the ports, the financial transactions are settling in correct sequence. None of this is guaranteed. All of it depends on a thread of technology that most people have never consciously noticed, and that the institutions responsible for managing it are only beginning to treat with the seriousness it deserves. What the GPS dependency story ultimately reveals is not a unique technological risk, but a repeating pattern in the history of critical infrastructure. Every transformative technology that becomes deeply embedded in the functioning of civilization goes through the same cycle. It arrives as a tool, it becomes a convenience, it becomes a standard, it becomes invisible, and at the point of invisibility, it becomes a vulnerability. Not because it failed, but because the systems around it forgot how to function without it. The response to that vulnerability, historically, has almost always been reactive rather than proactive. The first major failure reveals the depth of the dependency. The failure produces a policy response. The policy response produces investment in resilience measures. The resilience measures reduce the risk. This cycle is well documented across electrical grids, financial systems, water infrastructure, and telecommunications networks. There is no particular reason to expect the GPS story to be different. The question is simply, at what point in the cycle we currently sit, and whether the disruptions already on record are sufficient to drive the institutional response before a larger event makes the choice for us. That is not a question with a comfortable answer, but it is the right question to be asking. And asking it clearly, without exaggeration or complacency, is itself a form of preparation. The intellectual groundwork that precedes the engineering work, the policy work, and the organizational work that resilience actually requires.